First, a little introduction about the RQT Frame Editor. The Frame Editor is used for creating and rearranging TF frames. It offers convenience features such as copying full or partially poses, converting degree to radians, changing parents of frames interactively. It also features undo and redo functionality, and you can attach meshes to frames in order to quickly prototype your DFs. You can save your current configuration of frames, load them again, and also run without a GUI in headless mode. Additionally, most features are exposed as ROS services, so you can integrate them into your automatic workflow and call them from other scripts. Let's start with a short live demo. You can find documentation and full instructions for installation on the GitHub page shown before, where you can also give feedback and issues. Let's start with an introduction. You can see here on the left hand side the Frame Editor, and on the right hand side a setup with a UR robot which we can use for teaching. The window of the Frame Editor is split into two. The left hand side you can find frames you defined yourself with the Frame Editor. On the right hand side you can find all frames that are available through the TF system, grouped into the ones that are from the Frame Editor on top and all others on the bottom. By clicking on the frame on the left hand side, you then select the corresponding frame in Rviz, which you can move around as an interactive marker, as you know. When you select a different frame, you can then change this different frame as you know before. Like for example here, a new frame. Let's say we want to set the new frame to the end effector frame of the robot. For that, we first select the new frame on the left hand side, and on the right hand side we select the end effector frame of the robot. Now we can use the pose button to align our new frame with the end effector. We can also align single axes. So for example, in this case we can only align the x-axis. So by pressing on the x-axis, only the x-axis gets aligned, everything else will stay the same. If you have a lot of frames, a helpful feature might be to sort or filter for frames. For that you can use the search bars above the lists. The same feature is also available on the right-hand list of the TF frames. For each frame, you can also attach a mesh with different primitive shapes, like planes, or also more complex shapes. In order to see those frames, you need to add the corresponding marker visualization in Rviz. In this case, we first selected a plane, but you can also select other elements like a cube, arrow, or even a mesh. You can load STL files directly and also change their size and color. Here, for example, we loaded a mesh of a benchmark kit from the EU Robin project. As I said, you can freely choose the color of the object and also different levels of opacity. It fully attaches to the frame and also moves when the frame is moved dynamically in Rviz. So you can add new frames. Then for easier usage, you can also give it a name so that later on it will be in a collapsible group parent. In this case, we use the frame parent. Then for easier management, you can also add a group which will add the frame to a collapsible group on the left-hand side. When you now move the frame, it will always be relative to the parent frame, which in this case is the frame parent. So that also means when you move the parent frame, it will also be moving all the dependent frames. One of the more challenging things to do with TF frames is typically changing their respective parents. Here, the Frame Editor offers two different methods for easily setting the parent. One is by using the button Parent Keep Absolute, which will keep the absolute position of the frame while only changing its parent. As you can see, now the frame child 2 is not dependent anymore on the frame parent. The other is by using the Keep Relative button, which will keep the relative transform and only changes the parent. The Frame Editor also features an option to measure the distance between two frames, similar to the TF Echo tool. You can see it here, and you just need to select the two frames on the left-hand side and on the right-hand side, and it will give you the measurements. Another helpful tool is the conversion between degrees and radians, as you can see here. Of course, you can also always just change the respective values of the relative pose, for example, by typing it in with your keyboard. And of course, there's an undo and redo button to revert changes that you didn't want to do. You can launch the Frame Editor either by launching it in RQT or by launching it via a launch file. Here you have two options. One is GUI mode and the other one is with headless mode. You can load a configuration by selecting the YAML file that you saved. And then also you have a few options. For example, you can use the -s flag to do static publishing, or the rate option to give a certain value for publishing frames. The second package that I want to introduce today is the package Pitasc, which introduces a robot control framework that we developed at Fraunhofer IPA. So the software builds upon two pillars. The first is ROS with its driver layer for different industrial robots, and the other one is the algorithm Pitasc. Here you can see an example project with the company Rittal, where the aim was to cable terminal cabinets. We highlight the several elements of Pitasc, which is one force control, the other one multi-arm robot control, and constraint-based motions. Pitasc uses an external control unit, which is a PC or IPC typically, which controls the robots and also synchronizes robot movements over several robots, and also allows us to have several peripheral components such as grippers or force torque sensors. We developed Pitasc with a focus on assembly and disassembly tasks, so everything where the robot is in contact with its environment. One major component is force control and its combination with position-based programs. This approach offers us several advantages. One is the possibility to move adaptively based on the workpiece and feel differences in tolerances. With forces, we can directly verify if joint parts are connected or if the joining process was successful or not. With Pitasc, we still use the original controller, or we can still use it for transfer motions, for example, or robot safety, but we expand new capabilities. We can support several different robots, for example, universal robots, KUKA robots, Denso robots, or Franka-Emika robots, several sensors or grippers, and have easy integration, for example, in universal robot user interface. Here you can see a short overview over robots that we already used in our lab and integrated into Pitasc, force torque sensors that we used and have integrated into Pitasc, and several interfaces or grippers that we are using. We also provide a bridge to Siemens SPS via OPC-UA or also to other OPC-UA devices. Every hardware you can see here we've already used in our lab for several projects, public or privately funded, and we tested each thoroughly. Here you can see a list of processes that we already used Pitasc with. Among others, these include fastening of screws, and also unfastening, assembling parts by force control, plugging parts in and out, and, for example, dual arm handling of cables and tubes. Let me introduce now Pitasc on a technical level. As I said before, Pitasc builds upon ROS control and the robot driver itself. Robot programs can be defined as an XML code or with a Python interface. The program then gets transferred to a state machine which runs the robot program and controllers. You can add a lot of elements from the ROS world, for example, gripper drivers, if they expose a ROS service or ROS topic interface. Finally, Pitasc sent joint velocities to ROS control, which directly relays it to the robot driver. So in Pitasc, ROS control is only used for the communication and transport layer. Here you can see a more in-depth scheme. As I said before, the XML that you use to define a Pitasc program can either come from yourself or from a GUI. This XML then gets translated into a program model, which instantiates a state machine. This state machine then activates controllers depending on the current state and sends the commands to the drivers of the robot or the gripper. On the left-hand side, you can see the input and the output of Pitasc. Pitasc gets from the robot or the environment the joint values, or for example from force torque sensor the force values, and then calculates the joint velocity values that are needed to reach the goal. These are then sent to a robot or some other motion controller. So this could in theory also be a mobile robot, AGV or other. Pitasc uses a domain-specific language that is based on prototyping. Here you can see an example of a skill that creates a linear motion. The skill starts with the skill Cartesian, which just models the kinematic chain between tool and target. We can then add a position controller and make it a Cartesian tracking skill. So this way it can also send out values to the robot. Now finally, to terminate the skill, Pitasc uses monitors, which is a kind of like end condition for a skill. In terms of Cartesian tracking, it is a control error, and if the control error goes to 0, then the goal is reached. But instead of adding a position controller, you could also add a velocity controller, which then just also inherits from the Cartesian skill. The same, for example, you can also do with a force skill, where you first model the force measurement with the force skill, then use an apply force skill together with a force controller, and then also add a push duration skill by adding a monitor for duration. This highlights the three-step approach of Pitasc. First, encapsulate kinematics, provide the measurements, then add controllers, and finally define a stop position. Additionally, you can combine any skill that you like. Two examples here would be guarded approach and a skill slide. A skill guarded approach, for example, combines a velocity movement together with a measurement of force, which stops when a certain force threshold is reached. On the other hand, a skill slide combines the velocity feed forward together with an apply force in a different axis, of course, and together with a threshold in force for another axis, you get a guarded slide, which stops when a certain force is reached in a different axis. This lets you create very flexible skills in a very short time. Now let's make this example a little bit more concrete. Here I brought the example of flexible assembly of terminal clamps. The process of assembly can be split into 5 steps. The first step is pre-positioning of the terminal clamp. The second step is moving down until you feel a force. The third is sliding with the terminal clamp along the surface of the DIN rail until the hook hooks in and a little force notifies you that it has been in place successfully. The fourth step then requires pressing in Z and X direction while rotating around the point to pivot in the snap fit. Finally, we need to detect that the snap fit has happened correctly. Let's go into detail on what skills to use. For moving into contact, we can use a skill-guarded approach, which I outlined before. Then, also using a skill that I showed before, we can use a guarded slide to move across the surface until a certain force is shown. And finally, we can use the pivot skill with a monitor for snap fit detection to detect that the snap fit has happened. You can define skills just by copying the prototype, like on the left-hand side, if you don't need to define any more parameters. However, if you need more control, you can also set certain parameters, such as on the right-hand side, where you can, for example, use a skill sequence with several skills, and each skill has parameters such as, for example, the tool frame, target frame where to move, or forces. Let me show you how to create such a skill on the XML level that I showed you here. So we can start with a skill concurrency, which allows for the execution of several skills in parallel to each other. Let's start with a skill sequence, which executes skills in a sequence, and in parallel to it, a skill Cartesian tracking, which tracks with a robot tool a target frame in certain axes. Here we limit the movement to X, Y, and the rotational axis A, B, C. Now, first we want to move up with a certain velocity and then down with a certain velocity. For this, we are using the skill Cartesian velocity. One problem, however, is that these skills will not stop, so we need to give them an end condition. In this case, we are using a simple monitor, which is a monitor duration, which ends the skill after 2 seconds. There are many robot skills that we already implemented, over 50 actually, which also integrate different grippers, force torque sensors and other components. If you're interested in testing it out, you can register for our beta user program. Now let me show it to you live in action. Here I'm using the same setup that I used before with the Frame Editor, which is our tool for defining frames. Here you can see a very simple basic robot program in Pitasc. It is defined in XML and within 2 tags called Pitasc. The first tag models in Pitasc is where you can define included packages which you can use in your program. The prototype project defines a set of robot programs with the same environments and typically consists of 3 elements. The first is configuration, where you mostly can stick with the default configuration. Then there's the element environment, where you can define robots. And finally, the element applications, where you can define several robot programs. Here we have defined 2. One is simple forces, which is a skill sequence, and the other one is a skill move marker, which is also a sequence. You give each program a robot, which is the executing robot. And then within skills, you can define several skills. You can see here a few that are predefined. Here I want to start with the skill Cartesian tracking, which allows us to track a frame with a robot frame. This has several sublists. One, for example, is monitors, where you can define end conditions for the skill. The 2 required parameters here are the tool frame, which is the frame on the robot. In our case, it's tool 0. The other one is the target frame, so the frame that should align with the robot. Our VS Code language server lets us use a frame from the TF tree. In our case here I choose frame 2. Then we can already execute our skill. So we can use the RQT PyTeacher add-on, which allows us to load an XML file and then execute the XML file's program. You can see here are two applications corresponding to two buttons in the RQT PyTeacher add-on. So let's start the program and see what it does. Here you can see the robot aligns the tool frame to 0 with the frame 2. And if I move around the frame 2, the robot follows it. Also, it follows the orientation and all the things that I give to the frame. Because we use the skill Cartesian tracking, the skill never ends. So let's change this. So we can just replace skill Cartesian tracking with a skill in, which already has included a monitor. When we start the skill now, as soon as the robot reaches the frame, it stops the program. So let's add a skill additionally, which will be executed after the skill in. Here I choose a skill guarded approach. Here we need to first know in which frame we are measuring the forces. I'm using the frame 1 here. Then we can define the forces at which the skill will trigger and end. We also need to define how fast the robot should move in the direction. And of course, we need to also define a tool frame which the robot should move. And finally, we need to define an axis in which the robot will move. In this case, we are using the z-axis. And as you can see, the z-axis of frame 1 points up, which means the velocity needs to be minus 0.01 to move down. So let's see how the skill behaves. Of course, the robot was already at the position of the skill in, so it immediately skipped to the next skill. Now you can see that the robot will move down until it hits the ground and a certain force is measured. Now let's try it with a different frame too. Now let me show you how to combine several skills within a concurrent execution loop. For that, we first need to define a skill concurrency, which has a list of skills within the skills list tag. Here we want to use a skill apply force to press down in the z direction. For that, we need to define a force frame in which direction we are measuring the force to be applied. Let's use frame 2 here. For force control, we also need to define a compliance of the robot, which defines how hard the reactions of the robot are. and of course target forces which should be applied. Now we only defined the movement in one direction, but we need to define the movement in all directions. So we can just add a skill hold pose, which holds the pose in the same position as before. We just need to give it a tool frame so that it knows which frame to hold the same position. Now let's try it out. Now you can see the approach has been done and the robot pushes with a force of 10 Newton against the ground. Now let's say we want to slide over the ground. For this we can just add a skill velocity, which allows us to move across the ground while still pushing against it. As always, this needs a tool frame and a frame for velocity where we define in which direction the velocity is defined. We also need to give it axis in which the velocity is defined. In this case, we only want to define it in the y-axis of frame 2. Now we also give it a velocity, in this case 0.02 meters. Okay, let's see what happens. Okay, you can see the robot now pushes against the z-axis, the ground, and moves in the y-axis of frame 2. You can also interactively change the frame 2, so the robot automatically adapts into the direction. So you can automatically and dynamically change control frames and the program will adapt to it.